Hello, my name is Travis Vickerson, and today we're going to talk about safe lifting in relation to crane work using the TCIA Tree Care Academy Crane Operations Specialist. Safe lifting, we're going to look at load charts, load radius, and how we can calculate the weight of wood. So the first thing we're going to talk about is load charts. In a load chart, like the one here on this page, there's a very distinct dark black line on this load chart that goes straight through it. What that's saying is if you exceed the numbers above that black line, you will fail your crane, meaning you will break it. If you exceed those numbers below the black line, you flip the crane. Cranes are built on two principles, strength and stability. Therefore, our chart is built the same way. We have stability factors, which are above the black line. Structural factors, which are above the black line, and stability factors, which are below the black line. Some different load charts, different manufacturers will shade them one way or the other. Most of them, though, have just a distinct black line. This one does black line and shading in this picture here inside the manual. And what that says is, if this is our crane set up here and we're operating at this radius, if we exceed the load rated capacity at this radius and we're above the black line, we will fail the boom. Meaning the boom will break, it'll crease, it'll fall, it'll collapse. The crane will not flip over. However, if we exceed the weight and we're operating at a radius that's below the black line, then our crane has the potential to flip. Because our lever point has changed, now we are not failing the boom, we're just flipping the crane. So those are the two differences in load charts and how we deal with stability versus structural. We also have to look at the radius that we're operating at. All cranes come with a radius chart as well. This radius tells you at what boom length and at what boom angle, what radius you could operate at. We want to stay within 75% of our rated capacity when doing tree work. Some places will tell you 80%. I personally teach 75%. That's my personal choice. That's not an industry standard. Reason being is it's an easier math to do as an operator to do 3/4 of my capacity than it is to try to figure 80% of my capacity. I'm not that good with math sometimes. The cranes I've run haven't been the really, really fancy cranes where I can plug everything into a calculator and has the nice LMIs. They've been more the boom truck style cranes that have more basic load in moment indicators that don't allow me that ability to know that. So I've always operated with 75% of my capacity is where I'm gonna do tree work at. That gives me a buffer zone. That gives me the ability that if we have a piece that may be waterlogged, it may have some factors we didn't figure into our wood weight, and we think it's going to be 2,000 pounds, it ends up being 2,200 pounds, I'm still within capacity. But if I'm operating at 80% of my chart, and then we have something like that happen, I have a higher chance of exceeding my chart's capabilities, and thus either breaking my crane or flipping the crane. Greatest thing about a crane is I don't have to pick the piece up. The crane's going to do that work. So why chance it? Why push the envelope and do bigger and bigger pieces when we can just do one more pick? We have a lot of cranes that go over every year in tree care. A lot of them go over because of this reason. They try to go big with every pick, and they end up exceeding the load charts and flipping or breaking their cranes. So how do we figure out our weights? Ironically enough, way back when, Leonardo da Vinci had a theory of what's called symmetry in nature. What that theory stated is that a daughter branches cannot exceed that of the parent branch. So if my branch goes up and it's 6 inches around, and then it has a branch union that goes to two other branches, those two other branches' diameter cannot exceed that of the main parent material. If they did, the tree would fall apart. It wouldn't be structurally able to support itself. So there's some math that comes involved in this. For those people who enjoy the math, you can go out and try it out. I've done it at a college program I was a part of for a little while, and the math worked out for us. When you add up the diameters above a branch, they end up equaling that of the main branch. Now, obviously, where the branch union is at specifically will be larger because you have two branches coming into one. That area will be larger. But take your measurement 6, 8 inches below the union and then 6, 8 inches above the union and see if it works out for you. My experience has been that it works out perfectly every time. So in this picture here, in this image on the right-hand side, if you can imagine, that main stem comes up to the very first union. What this theory states is that that first union cannot exceed, those two branches, diameters cannot exceed that of the base. And then we continue to work that out the whole way of the branch of the tree. So a lot of times people are asking me how to measure weights and how to calculate weights. The easiest way is to figure out what a 10-foot section at a certain diameter is going to weigh. If you know that you're dealing on a 12-inch or 20-inch round tree, and you know that a 10-foot section weighs X amount on a 20-inch round piece. Well, if the union goes up and there's a union there, that two pieces can't exceed that of the 20 inches. So all I have to do is measure out 10 more feet so I can do a 20-foot piece. It can't exceed that. So what this is getting at is that you can do this all the way out to the farthest ends of the tips of the branches. If you were to take branches and if you could collapse them all together into one, taking out any void spaces, that diameter cannot exceed that of the parent branch it comes from. So this is able to do this where you can figure the math out pretty quickly, like the picture here on the right, all the way out to the tips. Adding all those diameters up cannot exceed that from where we're making the cut on that pick. Otherwise, the tree would not be structurally sound. It would fall apart. So it's a little bit hard concept sometimes for people to understand. I would challenge you on your work days to start looking at that. Start just doing some field testing. Make sure you're using the fact that combining two together does create voids because it's two round objects coming together. It creates a void. So you actually have to do the math principles of it, get the diameters and the radius and all that. But once you've done the math on it, you'll find that they equal the same amounts. And it's a very easy way to calculate weights. Because now I don't have to know what 10 feet at 6 inches weighs, and then 5 more feet at 3 inches, and 5 more feet at 3 inches, and then what that 5 more feet at 2 inches and 2 inches equals. I don't have to know that. All I have to know is that if I'm cutting a 6-inch stem, however long that piece is going to be, cannot exceed that of the 6 inches. Now, obviously, there's foliage weight that goes involved and water weight as well. We're only talking about how to calculate for the diameter right now. So before I move on from that, I want to make sure everybody understands that. Again, it's kind of a hard principle sometimes to grasp. So let's see if we have any questions about that and kind of make sure we've got that covered really well.
I don't think we have any questions about that. Stephen Connolly does bring up that union wood and compartment wood is exponentially heavier than a single log of the same diameter.
Correct. And that's where I said, Stephen, you're looking at the unions where the unions come together. It's going to be the heavier pieces. You have two pieces coming together, and you have to figure those in. The only way I have learned to do that is just off experience. I've tried taking the measurements of unions and applying the green log weight chart. It just doesn't work. I had to kind of just use experience on that. But the principles as far as the main stem pieces, that has held true for me so far. So we're going to talk about some wind. That's our next part, dealing in wind. Every manufacturer has different recommendations for how much wind you can operate in and how much wind you can't operate in. Look at your manufacturer recommendation. Usually bigger cranes have got anemometers at the very tip, which tells you how much wind the tip of the boom is receiving versus at ground level. So follow the manufacturer recommendation. Just remember that when you have a load hanging off the end of your load line, that's acting as a giant sail or a kite. So any wind you're going to be getting is going to be much more highly felt by the crane because you have this big catch for wind here. And that's how you easily can get some swing going, which creates side loading on your boom. Crane booms are designed by physics to operate in the load under position, not load beside position. So when you're starting to pull your load from one side to the other, you can have a lot of failures pretty quickly there because that's not how the way the crane's physics and engineering work. So that's kind of the wind stuff. We're going to hop onto soils real quick. Talk about some soils, and then we're going to come back to soils in more depth here in a minute. So some quick numbers to remember, if you can commit them to memory or take a picture of it, is load-bearing capacities for soil. The very first one is undisturbed soil and lawns. Undisturbed soils and lawns operates at 22 psi. Asphalt's 29 psi. Clay and silt is 43 psi. Mixed granular is 51 psi. Firm compacted gravel is more of like your construction type sites. It's more your engineered gravel sites for setup. That's 58 to 109 PSI, depending on how much aggregate they do or don't have inside the mixture. And then concrete is 1,000 PSI on an 8-inch depth pour. The top picture on the right-hand side I took while I was in Knoxville, Tennessee one year. That's actually from the off-weight side of a link belt 60-ton crane. They were picking off the driver's side of the crane. And this outrigger's on the passenger side of the crane. They put the outrigger straight down onto the asphalt and had about 1 inch of depression in that asphalt. So even though they weren't picking weight over that side, just the weight of the machine itself created about 1 inch of compression in the asphalt, which is enough to put the crane out of level if they're not careful. Big thing here is just understanding how much PSI your crane's distributing to the soils, and we're going to do the math on that in the next section, and how we can overcome some of these soil setups. So also in safe lifting, we want to talk about dynamic loading. Dynamic loading is when you accelerate a piece too quickly or stop a piece too suddenly. What thus happens is if I move my crane too quickly and drop my piece as such, the effective weight that my crane is actually feeling is much heavier than that of the actual weight. And that's where a lot of times we'll see these booms crease, like in this picture here, is because our operators are either A, hoisting too quickly or stopping too suddenly. So if I have a 500-pound load on here and I try to snatch it really fast, the crane's going to feel much more weight than first trying to move that weight. If I pick it nice and slow, the crane will feel the actual weight to it. The same is the reverse of that. If I have a 500-pound load on here and I'm slowly lowering it and I just stop and shock load my crane, the crane will feel that this piece weighs much more than 500 pounds. All right. This is very important in tree work because a lot of times we're cutting, rigging things from a tree. And if we're not making sure that our loads are very stable, all of our picks are very stable, you run a much greater risk of dynamically loading the crane and how the piece comes under tension of the wire. I've sadly seen some people doing crane work that have actually used felling notches and have felled tree stems into the load line and shock the whole crane. You hear the wire slapping the top of the boom, and very bad things are occurring. This dynamic loading the crane. What you're having there is that effective weight that's being felt is much higher than the actual weight, and you'll exceed your capacities in your chart, creating a structural failure or a tipping and a stability failure. All right, we're gonna talk about setup real quick. So now we talked about the PSI. We know how much we're good for on PSI of our different soils, be it lawn, be it aggregate, be it concrete. But now how do we get over? How do we correct those problems? All right. These next photos, I was given permission to share. Some people have probably seen these photos. They just recently were on the internet, on the Facebook, in relation to a crane that went over in New Jersey. So just going to share these. So don't anybody harass me for them. All right. But what happened here is the crane was set up operating in a backyard situation. The outrigger was put roughly about 3 to 4 feet from the foundation, set up on top of mulch. There obviously something occurred. The outrigger sunk. The crane ended up tipping, going over. So there may have been a void space. There may have been some compaction issues. And if you'll just keep clicking through those photos real quick there, Kale, get to 27 for me. All right. You can see how much the outrigger sunk in. This is not an A-frame outrigger. This is what's called an out and down outrigger, which is the exact similar to what we have here, where the outrigger comes out from the crane and then goes down. However, in that picture, it makes it look like it's an A-frame outrigger where it comes at a 45-degree angle. That's how much failure occurred in the soil due to a void space, due to a backfill, and some other things. Setting up that close to the foundation, there are some setback issues there that we had to look at to try to correct those things. Number one way we correct for our cranes and is dealing with PSI is in our dunnage. So not our tonnage. Our tonnage is what the crane can pick. Our dunnage is what we put down underneath our outriggers to displace weight to our soils or to gain height in order to level our crane. You achieve the same thing from both operations, but it's two different purposes. As you can see here, the crane I have set up here, where I'm using some cardboard as my dunnage, roughly 2-inch by 2-inch pieces. And I've got them stacked 3 high in order to get enough level to get all my tires off the ground and get my crane level. And I was able to level the crane just by doing that. Unfortunately, it's not always that easy. Most time we're using actual wood material, wood or synthetic material. There's been a lot of discussion over the years in regards to box style cribbing versus flat cribbing. Both of those shown in this next photo. The one on the left was a 3x3 box cribbing. That 3x3 is like building Lincoln logs. You're literally stacking 3 pieces on top of each other. All right. Each one of those points of contact has a PSI rating. All right. This is a Douglas fir. Douglas fir has roughly a 500 PSI shear strength. So when we figure that math out on a 3x3, meaning 3 pieces, put it on top of 3 pieces, we're at 6,000 pounds per contact point, 9 contact points. And that cribbing and that style, that box style cribbing, is good for 5,400 PSI before failure. Now, if we did the exact same size cribbing, which is 4-inch by 4-inch wood, and we did a 5x5, meaning 5 pieces on top of 5 pieces being perfectly level and full contact, we're at 150 PSI. Now, that's not 150,000 PSI. That's not 150,000 PSI of soil displacement. That's shear strength of the wood before the wood fails. So if we have to gain height, it is perfectly acceptable to use the box cribbing style cribbing to gain height. But I highly recommend that your first level and your top level be solid pieces slammed all together. That provides the most stable footing. And then in the middle between those two solid pieces can be the box style cribbing, be it 3x3, 4x4, or whatever you need to do. But just make sure that the amount of contact points equals the amount of weight our crane weighs and how much it's going to be lifting. So therefore, we don't have a shear failure in the wood. All right, so the next thing we're going to look at is how much PSI does our crane displace to the soil. So now we've talked about how much PSI our wood can handle, but now we're trying to make sure we're dealing in the correct PSI to our soil. As we talked about earlier, we're operating, say, a lawn, or say we're operating an asphalt, which is 29 PSI. We want to make sure that the weight of our crane plus the heaviest pick we're going to do, if we're over top of one outrigger, so if we're over the top of this corner outrigger here, can displace enough ground pressure to not fail the soil that we're operating on. So in order to do that, what you need to do is you take the weight of your crane, the weight of your crane divided by the number of outriggers, and then whatever your heaviest weight's going to be to do the point loading. So if our heaviest load is going to be 10,000 pounds, for instance, we figure out the weight of our crane divided by our number of outriggers. We add 10,000 pounds because that's the max weight this one outrigger will feel if we do what's called point loading, which is where that one load is directly in line with that one outrigger, is point loading. From there, we have to look at how much we're getting, how much pounds are per outrigger. Then we figure out the square inches of our outrigger support, meaning how much material we're putting on the ground here. If we're using a 2-foot by 2-foot size piece of wood, for instance, or a mat, or cribbing, wood cribbing that comes in 2-foot by 2-foot length, you're at 576 square inches. So now all you do is take the max load that one outrigger is going to feel, divided by the square inches of outrigger displacement, gives you how much PSI is being translated to the soil. So hypothetically speaking, on this crane here, if this crane weighed 370 pounds, and our heaviest pick of the day is going to be 10,000 pounds, that gives us a total weight of 89,370. We then divide that by the 4 outriggers and gives us an individual point load of 22,342.5 pounds. 2-foot by 2-foot outrigger pads gets us 570 square inches, gets us down to 38.78 PSI, which is fine if we're operating on a clay and silt soil. But if we were setting this crane up on asphalt or a lawn, we would actually fail the soil at that displacement. We would need more wider dunnage laid down in order to get a lesser displacement to get the PSI to a better rating for that soil. So that's just a real easy way to figure out how much you're displacing to the soil and how to figure out to lay down the right cribbing or the right style in order to get the right displacement for that thing. As you can see in the next photo, there's different ways to do that by using solid matting style, which is wood that is bolted all together to create one layer. You've got all tour mats or the those big yard armor mats now. You can do it that way. Or you can just use regular 4x4, 4x6, 6x6, 6x8, 8x8 timbers. Works as well. In this photo also, you see that there is what's called a leveling block in the middle photo. What that is, if you have an uneven area, you can either dig it out or you can put what's called a leveling block in. It's kind of hard to see from the pine straw in this picture, but there's actually another leveling block, another towing block further under there that in the event that those materials start to collapse, it'll actually engage that other block underneath there and prevent a failure straight down. But that's perfectly acceptable. You can see the stack cribbing in this photo here in order to gain height, in order to get this crane level, had to get pretty high. The biggest thing is we have to understand that when we have displacement, that displacement is not uniform. It's like dropping a pebble into a stream or into a pond. When you drop that pebble into a pond, those rings go out and dissipate. The same thing's occurring from the weight of our crane. As this load is being loaded here, the weight's being translated to our outrigger, and that weight is radiating out from our outrigger in a uniform fashion. As that radiates out and comes in contact with an object, it's going to apply pressure differently as it comes in contact with that object. Thus, how we get to setback. So in the photo we looked at of the crane that went over earlier on in this module, they were about 2 to 3 feet from the foundation wall. Now, in talking to the people who were on site, they didn't have any failure of the actual foundation wall. So they didn't collapse in the basement. They didn't collapse in the crawl space. Most likely what occurred, there was some void due to that being new construction and the soil not being compacted well enough around the foundation. Found a void and collapsed the void. When we know setback, there's 2 different principles used with setback. If you know the depth of the object in the ground that you're setting up next to, you can be 1 times the depth away from that with your outrigger. If you don't know the depth though, it's 4 times whatever the widest part of your dunnage is. So on this crane here, if we're using the 2-inch by 2-inch cribbing I have set up, we just do that times 4, tells me how far I could be from an underground object, be it a terrace wall, an excavation, a vault, a foundation, any of those things that go underground. Because as you can see in this photo, or this image, as things go outward, they displace energy. As they displace energy uniformly, things come into contact here and then a little bit off, and that pushes against the wall. So that's why setback is so key and so important. Thank you for tuning in for this module. Hopefully you got a lot of information out of it and can utilize this information to help you complete the Tree Care Academy Crane Operations Specialist book.